here, that's perfectly fine. This solution is 100% spot on, but we can just use a couple of small rules in order to make this look a little bit nicer. Okay, so the first thing I'm going to look at is this sine component. So we have sine of n plus 1 over 2n times by pi. The first step here is I'm just going to draw this this division by 2 over to the side here, and we have n plus 1 over n. Simple step. So then if I just expand this fraction out, we have sine of 1 plus 1 on n times by pi on 2. So then if I expand those brackets out, we have sine of pi over 2 plus pi over 2n. So the reason why I put it into this form is that I'm going to use, what is it called, the sine angle formulas. And we can use sine of a plus b to expand it out into this form that we have here, which is sine of a cos of b plus cos of b sine of a. So that is sine of pi over 2 times by cos of pi over 2n plus cos of pi over 2 times by sine of pi over 2n. Now sine of pi over 2 is just equal to 1, cos of pi over 2 is equal to 0. So therefore, this term gets stripped away because obviously anything multiplied by 0 is 0. The 1 multiplied by just results in this term here. So we have cos of pi over 2n. So that means here, this term here gets reduced down to a simpler form. We haven't been able to flip it yet, but at least we've taken it from a more complicated form to a simpler form. As I said, this is perfectly fine as it is. This is just me sort of, going a little bit further. Okay, so the next step that I'm going to use is I'm going to try and move this from the denominator up into the numerator. And I'm going to use the exact same law that we drew it on before, Euler's reflection formula when applied to the gamma function, which says gamma of z times by gamma of 1 minus z is equal to pi over sine of pi over z. So therefore, coming down here, if I have z is equal to 1 over n, that means that gamma of 1 over n times by gamma of 1 minus 1 over n is equal to sine, pi over sine of pi times by z, which in this case is pi divided by n. So if I rearrange this into the form of 1 over gamma of 1 minus n, and I'm obviously doing that because of what we have here, that becomes gamma of 1 over n times by sine of pi n over pi. So what I've been able to do is by employing this function here, this identity here, the Euler's reflection formula when applied to the gamma function, I've been able to take this 1 over a gamma expression and put it onto the numerator. So again, this is just a personal preference. I like to do it that way, but you don't have to do it that way. Okay, so this original expression that we have for our solution, pi over 2n times by sine of n plus 1 over 2n times by pi times by gamma of 1 minus 1 over n, all I've done here is just separate it out into its individual components. So we have pi over 2n times by 1 over sine of n plus 1 over 2n times by pi times by 1 over gamma of 1 minus n. The reason why I've done this is because we've examined each component individually, so it just makes it easier. So this is equal to pi over 2n times by this quantity here, as we went through up here, becomes cos of pi over 2n. My apologies, I've got an extra bracket here. I must have made a mistake with my latex, so just ignore that extra bracket. And then 1 over gamma of 1 minus n, which is this quantity here, which is what we have here, is replaced here. So what we see here is this pi cancels out with this pi here, and so we're left with gamma of 1 over n times by sine of pi over n over 2n times by cos of pi over 2n. And again, remember, just ignore that extra bracket. Now, this, you may look at this and go, well, this doesn't really seem to be much simpler, but thankfully there's an extra bit. If we have a look here, we see that with our sine term here and with our cos term here, the cos angle is just this angle divided by 2. And so immediately I go, oh, what if I should be able to apply the sine double angle formula? And that's what we're going to do here. So sine of 2 times a is equal to 2 times sine of a cos of a, which means sine of 2 times by pi over 2n, which equals sine of pi over n, which is what we have here on the numerator, that's equal to 2 times sine of a, which is sine of pi over 2n, times by cos of a, which is cos of pi over 2n. So now what I'm going to do is I'm just going to replace this term here with this term here. And so the original form that we had, which we repositioned into this form here, is equal to, so we have gamma of 1 over n times by, and again, sine of pi over n gets replaced with this, so 2 sine of pi over 2n times by cos of pi over 2n, and then the numerator remains unchanged. Now, again, the reason why I'm doing this is because I'm trying to get rid of this function on the denominator. And thankfully, just with the form that we have here, there's no absolute reason that, or definitive pattern, at least that I'm aware of, that would take me to looking at this and going, I can definitely reposition it into this nice form. It was just I was playing around with the algebra and I found that it could be expressed in a simpler form. Okay, and so we're able to cancel these out, and so thankfully now, not only can we cancel out the cos term, we can also cancel out the 2, and the beautiful thing about this is we no longer have any functions on the denominator. So we've gotten rid of the sign on the bottom and we've replaced it with something on the top, which is fantastic. As I said, that's what I was aiming to achieve. We've also been able to take the gamma from the bottom and put it up onto the top in the numerator. Again, that was something that I was hoping to achieve, and thankfully we were able to do it. And so we're left with 1 over n, which is just that n term here, gamma of 1 over n, which is what we have here, and then the remaining term is just sine of pi over 2n. And so we've taken this expression here, and not only does it look a little bit nicer, not that looking nicer is better, but again, we're not doing the division by anything, and I like that. So anyway, okay. And so, therefore, the integral that we had, j of n from 0 to infinity, which is the integral, from 0 to infinity of sine of x to the power of n dx is now equal to 1 over n gamma of 1 over n times by sine of pi over 2n. And as we went through, this is for n being a real number, where n is restricted so that it cannot be a value between -1 and 1. And so that is the final solution. Now, I'm just going to include, if you want to stop there, that's 100% fine. In one of my other videos, I examined the integral from 0 to infinity of e to the negative x to the power of n. And it actually equals this component. So as soon as I saw the solution, I was like, oh, wow. We see that we have this direct relationship between the integral from 0 to infinity of sine of x to the n and the integral from 0 to infinity of e to the power of negative x to the power of n. Now, this is actually fairly obvious when you look at, say, Euler's formula when it comes to complex numbers, and we can actually see that there is a direct relationship. So what I was able to see here, which is fantastic, is, I wonder what happened here. Oh, actually, you know what? Just leave it. Ignore that bit. Something's gone wrong with the compiler here. I'm not 100% sure why. So let's just ignore that little component and just leave ourselves with this solution here, which is j of n, which is the integral from 0 to infinity of sine of x to the power of n is equal to 1 over n gamma of 1 on n times by sine of pi over 2n. And again, that's for a real value of n where n cannot be between -1 and 1. Okay, so I hope you've liked this video. If you have, could you please like the video? If you would like to see more videos like this, please subscribe. As I say in all of my videos, I take requests and please critique away and let me know. So if you have any suggestions for certain families of integrals or certain types of integrals or whatever that is integration based that you would like me to cover, please either comment here, send me a direct message, and if I am able to actually solve it and I have time to be able to do it, I'll certainly post it up. I haven't received any yet, but certainly within time, when I do receive them, I will post them up. Until then, I'll just keep finding integrals that I think are interesting to cover. Okay. All right.